memory, we were in chapter 6, Hawking radiation, section 2, called Bogoliubov transformation and thermality. And the section has different subsections. The first one was to explain you what the model I'm going to use. And remember that in order to be able to do everything analytical, I was simplifying drastically the space-time. So I was considering still the process of collapse of a black hole, but just gluing a Minkowski portion with the Schwarzschild portion. And physically that represents a black hole formed by a spherical shell of radiation collapsing. And the metric, of course, in this infinitely thin is not smooth. The derivatives are not, it's continuous, but the derivatives are divergent. But we make this just smooth profile, everything would be fine. And here we had in Schwarzschild we had coordinates r out, u out, and angular coordinates. In Minkowski region we have r in, u in, an angular region. And remember that demanding that the metric is continuous, we found an important relations between in and out coordinates. R in at V naught has to be equal to R out at V naught, and from that we obtain that the relation between the U's has this block, which is going to be quite important for Hawking radiation, where VH is just the null ray that forms the horizon.
I have a question on that. So are those two divided? But is the in divided by region, or is the in mean what have to do with its initial conditions?
No, that is just the Minkowski region or the Schwarzschild region. They are calling an out coordinates, but they are really the whole Minkowski and the whole that.
Okay. Thanks.
And I was pointing out that this when u in or when u out goes to minus infinity, that goes to u in. So here, the u in and u out, they have a linear relation, and is when u out goes to plus infinity. So what we are talking about u's close to this region, in this last part, where the log dominates. And that is, as a consequence of that, Hawking radiation only will appear at large values of u in that region. This is why I emphasize that here, because it will be important for Hawking radiation. And in the second subsection here, we were talking about the Bogoliubov transformations. And we argue that we are going to because the space-time is dynamical, there is no global time-like symmetry, so there is no a single preferred representation. But time-like symmetry arises in the future and in the past, so we can find these two preferred representations, the in and the out, and our goal will be to relate them. And the physical problem will be to choose the in vacuum initially, let the black hole to be formed, and then ask how that in vacuum looks at late time. So this is what we want to compute. And we already discussed last day what is the in Fock representation. And remember, it is characterized by choosing as the basis of positive frequency modes that oscillate with positive frequency in the past. So modes selected by the time-like symmetry in the past. Mathematically, in Scri minus, these guys behave as a simple plane wave. It's a simple oscillatory wave with spherical harmonics carrying the angular coordinates, and r over there, and 4 pi omega to have them normalized. If they are normalized initially, they are normalized forever because the wave equation preserves them all. And today I want to start. So with this, we define the fog, the in fog space, and the in vacuum. The in vacuum is the state having no quanta on the infinite past, where the space-time is like Minkowski. So this agrees with the Minkowski vacuum every now. So now we have to repeat this analysis. So we stopped here last day. So now it's new material. Now we have to go to the out representation. And you can already imagine what's going to happen. And is the representation single out by time-like symmetry in the future. Arising in the remote future. So just what we did here, but going to the future. After the black hole has formed, if you wait long enough, the space-time is stationary again. There is a time-like vector field on that region. And in fact, if you go really far away from the black hole, you in fact recover the whole Poincare symmetry because the space-time goes to flat. But as you know, we only need the time-like symmetry to define a Fock representation. So all what we have to do is to repeat what we did for the in, what we did for the in representation by replacing square minus with a square plus, and in square minus we had the coordinate v. In square plus we have the coordinate u out. Wherever you see v, replace it by u out, and you will have the construction. In other words, the positive frequency modes that are going to define the out representation are exact solutions to the Klein-Gordon equation. So they are they are exact solutions with initial data. So we define them via the initial data. The initial data that we want is that in scribe plus they behave as positive frequency modes with respect to the natural time depth, which is u out. Remember, u out is just t out minus r star out. So they are just positive frequency modes. And spherical harmonics covering the angular dependence, and r out with a 4 pi omega. And the same for the derivative. And the derivative with respect to u out, initial data is given by the function and the first derivative. Square plus has to be minus I omega, the mode itself. That fully characterizes our modes. So same logics as before, nothing different. However, there is an important difference between square plus and square minus. Crucial difference. And I already mentioned it last day. Important difference between square plus and square minus. And is that while square minus is a Cauchy hypersurface of the full spacetime, square plus is not. square plus is not a Cauchy hypersurface. There are many geodesics that don't go, that you extend as much as you want. They go inside the singularity, and therefore they never reach A plus. Therefore, it is not true that every inextendable geodesics crosses a square plus. Therefore, it's not a Cauchy hypersurface. So, therefore, this basis, together with the complex conjugated, cannot be a full basis of the space of solutions, because any solution with support inside the horizon cannot be expanded by this mode. These modes, they don't have any support inside the horizon, so they cannot expand modes with support over there. Therefore, that is not a complete basis, which is just a consequence for that. So the modes out, together with the complex conjugated, for every omega, L, and M, are not a complete basis of the space of complex solutions to the planar line. We need modes with support inside the horizon. But the solution is simple. The solution is, what can we add to a square class to have a complete Cauchy hypersurface? So if we have a square class here, it's not a Cauchy hypersurface, but it is quite obvious that if I add this, the horizon itself, so that square class union with the horizon is a Cauchy hypersurface. And I could choose another extension like that, and like that, and like that, but the horizon itself is enough. So, therefore, if we add to this basis a basis of modes with support in the horizon, we will have a complete basis. So to complete the basis, we need to find a basis of positive frequency modes with support in the horizon. Suggestions for that, how we construct that.
Positive frequency modes in the horizon.
Positive frequency. Remember, every time I say positive frequency, I mean positive norm. So, can you tell me which basis of positive frequency modes would you use for that with support on the horizon? In the square class was clear. We had a Killing vector field, time-like Killing vector field, that one. So the modes with positive frequency with respect to it.
In modes.
Sorry?
In modes. In mode should match there, right? So at the horizon.
But in modes, they are really far from they are defined here. So at the horizon, they
will change.
They will be
something else.
Something else. I mean, here everything simplifies because we are neglecting the potential.
In reality.
But you can propagate those in modes there, and that would be a possibility.
You want light rays that are going outward towards square plus, right?
No, I already have the modes going square plus. So now, in order to have a complete basis, I need modes which are
okay.
with positive norm, and then they together will form a basis because this is a quantification process. They have to be orthogonal. They are going to be because they have support in the joint region. So the integral which is the inner product, is a spatial interval with space 0, of course. But there are infinitely many choices. So the point is that the horizon is not, or the geometry around the horizon is not stationary at all. The geometry around the horizon, around H, is not stationary or static. You can see the curvature before this line is 0, and then the curvature is not 0. So you know, along that hypersurface there is no any kind of like symmetry or nothing like that. You know, the geometry on this vicinity is changing dynamically. So we don't have a killing time-like vector field to choose a preferred set of modes. Therefore, we have ambiguity. There is full ambiguity in what we choose as a basis of positive frequency modes. Ambiguity in the choice of positive frequency. In fact, strictly speaking, there is no solutions here which oscillate with positive frequency because the time is dependent. So therefore, there is ambiguity also in the notion of particles, as we have discussed in chapter 4. That is the same. So every time you listen somebody discussing particles of Hawking radiation crossing the horizon, what do you mean by a particle there? There is nothing that I can call a particle there. You can define, you can use some modes, and for you a particle is something, but you can use other modes, and for you a particle is something different. Everybody would agree what a particle is in a straight class, because we have symmetry there. But in the horizon, there is no canonical, natural, or preferred notion of particles. So
That ambiguity happens along any other ray going out in this direction, right? So why do we say the Hawking radiation happens at the horizon?
we don't say that Hawking radiation happens on the horizon.
Okay,
Hawking radiation is something that you measure at the straight class by definition.
okay.
So, and we will go over that. So Hawking radiation is a statement on a straight class. And there is no well-defined and ambiguous notion of particle at the black hole. So this picture of Hawking radiation as a pair of particles, one goes inside the black hole, the other escapes infinity, that you find in many popular articles, that is heuristic. You know, rigorously speaking, there is nothing that you can call a quanta or a particle at the horizon. There is full ambiguity. So, therefore,
So like when people say that light goes inside black hole,
say it again.
I mean light goes inside black hole, it won't be coming back. So is that also ambiguous statement?
Light becomes goes inside the black hole.
Yeah.
But you know, if you have a laser here, really far from the black hole, you emit, you count the number of photons, 1 photon, 2 photons, then you are really far from the black hole, there is some time-like symmetry, you know what a photon is, has definite energy, but as you go closer to the black hole, the geometry becomes dynamical, and then the notion of photon, there is no well-defined number of photons. I mean, the energy is exactly the same, you know, the momenta is exactly the same, which is, you know, those quantities are observer independent, but the number of quanta becomes ambiguous. That depends on what you call a quanta, and there is no preferred basis for that.
Isn't it the geometry, is it not static? Like there is a discontinuity, but it's curved on that side. And
Right, in this simple example is static here and here, but it's not globally static. In a real situation where this is not just glue, will not be static. So the key point is that it's not static, so we cannot define. So therefore there is ambiguity in the Fock representation, in this part of the Fock representation. So our Fock space will be a combination of this one and this one, our out Fock space, but there is ambiguity in this one. So our choice for positive frequency modes at the horizon. I will call them phi int, where int stands for interior, because they are modes which are going to have support in the interior of the black hole, in contrast with out modes, which never had. Is going to be by mathematical convenience. Our choice is going to be based on mathematical convenience. Oh, I forgot to say something. So I can do it here. Doesn't matter. You know, I'm going to make a choice because I have to do the calculations, but that choice is not preferred anyway. You know, any physical prediction I'm going to make with that is not really physical because it depends on my choice. Fortunately, observations at scribe class are insensitive to which basis we choose over there. Insensitive to our choice for these modes. So whatever we choose, any the statements about physical processes happening in the scribe class are not going to be affected. And in particular, Hawking radiation has to do with scribe class, so it doesn't matter which basis we choose, Hawking radiation is going to be exactly the same. So this is why I can choose just whatever I want. So this is what we are going to do. So a mathematical convenient choice is the following. So our choice, and I think it was first used by Parker in 1975, and Walt also at the same time. These are the two papers that follow Hawking original paper, and they just reinforce Hawking's result, and they both use as a useful choice of in modes this form, which now may look artificial, that you will understand later on how they were motivated by this particular choice. VH minus 2RS log V minus VH divided by 2RS times delta V minus VH.
Is it phi in
So
dagger,
delta or theta?
dagger or phi in here?
In, no dagger. And this is a function, so dagger is
And
for operators.
that is delta or theta?
That is theta. That is it. And as usual, I forget always divided by R. R, remember, R is always R out if you are in the out region, in the Schwarzschild region, or in the Minkowski region. And I forgot the angular dependence, which is also spherical harmonics. And this Heaviside theta is needed because these modes are only defined. Remember, this is VH, so these modes doesn't need to have support for V smaller than VH. So they only have support in this part of the spacetime, and they are incoming through the horizon. So this is why this theta is here. So it's needed. And of course, one can build wave packets from them just by integrating on omega with a function of compact support in omega. So they are purely ingoing at the horizon. So now that we have these modes, the in and out modes, we have a full Fock representation. Alternative to the in one, and this is what I'm going to use to derive Hawking radiation. So, therefore, the modes out omega L m together with the int modes for all omega L m plus their conjugates.
Wait, I don't understand something right on the board over there. How can you have ln of v minus vh theta v minus vh?
Say it again.
So there's ln of v minus vh, and then there's a step function of v minus vh. What's the,
So I have
what
this
is that?
That's all in the exponential. Under it is just under it.
right. This is the exponential. Is that I was, and this is just multiplying the exponential.
Okay, so what does the
It's
step
okay.
function do?
That you know that you cannot use v smaller than vh.
Oh,
That
okay.
For v smaller than vh, this guy is 0.
Okay, so it's
It is only
It-
supported in this portion of the spacetime. Which is
Oh,
v smaller
okay.
than VH.
thanks.
It is 0 if the v is the other way. Thanks for asking. So therefore, out modes, which are outgoing waves in the infinity, future infinity, and in modes, together with the conjugates, are now a complete basis of the space of solutions. And as we described in detail in chapter 4, then they provide a natural, they provide a splitting of the space of solution in positive and negative frequency modes. Now the positive subspace is made of two subspaces itself, the ones going from here and from here, and the negative one, which is the conjugate of the positive, is just also made of two portions, where this is the out part and this is the in. Sorry. No.
So that set is the basis of only S plus or the full SC.
Say it again.
Therefore, that set of phi out and phi int, since are those both positive frequency modes?
Yes,
or-
they are both positive.
So then they're a basis for S positive, the
Right.
whole space.
Plus
but-
their
Plus
conjugates.
their conjugates.
Oh, plus or conjugate.
Right.
Cool.
This is the positive frequency subspace, this is the negative one, but each of them is made of two parts, one coming from the out modes and the other coming from the in modes.
Yeah.
Int modes. With this, we can define the one particle Hilbert space. Hilbert space that will be a product of the out one and the in one. So quanta with particles associated with this solution, and quanta with particles associated with the other solution, and the focus space, which is going to be a product of the in and out sub-focus spaces. This one carries the degrees of freedom that goes inside the horizon. This guy carries the degrees of freedom that goes to infinity. And then, so we can call this the out int representation. And it's a fully valid representation, as good as the in one that we defined before. In particular, it's not difficult to write a representation for the field operator, we have done before, which is a sum on the basis of modes, positive frequency basis, annihilation operator for the two parts, the in and the out. In omega. Okay. In omega L m plus the conjugated with creation operators. a valid representation for the field operator, and the vacuum, as you can imagine, the vacuum is going to be a product of the vacuum with respect to the two sets of balls, out and in. And in particular, something that will be important is that the out piece, just because the way it is defined, the out part agrees with the, if you want, the Minkowski vacuum at straight glass. The Minkowski vacuum in a straight glass. So agrees with the standard preferred notion of quanta of particle far into the future and far from the black hole.
Maybe this is a dumb question, but I find it surprising that you can take the positive basis of both of the two subspaces out int things and get something that has, does that itself have a positive basis, or?
I don't get the question.
I guess what I mean is that, are you dividing it into a positive basis and a negative frequency basis? Is that two sub-expressions up there, like positive?
This here.
Is it true that S out positive times S out S int positive is equal to some sort of positive frequency sub-basis of the whole space?
This plus this.
Yeah.
So, yeah, yes, this is like, you have the whole space of positive frequency modes, which is this one, and you can divide it in two orthogonal subspaces.
So that actually does divide up like that?
Yes.
Okay, and then you can divide it that way and then form the products between those two sub-products?
I mean, it's sum, it's not product, it's a sum.
As a sum.
So it's like, if you take R2 and you say that R2 is this subspace plus this subspace. They are orthogonal, so R2 is the sum, direct sum of the whole plane. You can get it as the direct sum of one and the other.
Oh, okay, sure, so it's just like adding another fourth dimension, so
Exactly.
it doesn't matter
You are
which
dividing.
dimensions you add to which dimensions.
Exactly.
Okay.
So it's the direct sum of those, is the whole. It just happens that the positive frequency subspace, the whole one, has a natural division between these two orthogonal ones.
Okay, thanks.
Sure. And
So what's the difference between that and the product that you're writing with the vacuums? I don't quite understand that.
we can discuss that later.
Okay.
The difference between direct sum and direct product.
Yeah.
They are two different things.
Yeah.
The same as the sum and the product are two different operations. The same happens for sum. We can discuss it later
Okay.
in detail. So direct sum is just taking all possible linear combinations of that. And direct product is something that's slightly different. Okay, and as you can imagine, the creation and annihilation operators, out with out, they have the standard relations. In with in, they have the standard relations, and out with in always commute. Just because remember, the commutation relations are given by the inner product between the bases that define them, and the bases out and in are orthogonal to each other. So I don't write that, but that is yeah. Okay. So to be fun, because I put the wrong numbers in my notes, so now I have to find what is the next. Oh no, this was right. Okay, so we have now defined the in and out representations, which was the goal of this section, this subsection. So let me go to the third part of this section, which is now compute the Bogoliubov coefficients. And now remember, we have two representations for the quantum theory. We have the in representation, which is obtained using as our basis of positive frequency modes the modes in that we defined before, and we have the out int representation, which is choosing as basis of positive frequency modes the combination of out and int modes. And we want to find, the Bogoliubov relations, coefficients relating both bases. And you know that they are defined by the following. What we have to do, for instance, we can write the first line, the in mode modes together with the conjugates are a full basis, so I can express the out mode as a combination of them. So I have to sum over the in basis. Let me put primes, and it's going to be some coefficient having log of indices. 3 indices for the first one. In fact, the first one has an additional index out, and 3 indices for the basis, the in mode plus another coefficient times the in mode conjugate. Again, they are a complete basis, so this is always there are always coefficients alpha and beta, and they are unique, satisfying this relation. This defines what we mean by alpha out and beta out. Exactly the same is true if we replace out by int. So there are also alpha int, alpha prime, a prime in. I am getting tired of writing too many indices. Plus beta in omega L m omega prime prime in is going to be omega prime. So this is what defines alpha and beta, and we can obtain them, alpha and beta, just using the orthogonality of the basis. So if I multiply phi out by the in basis, I can take out alpha and beta. One thing, the dependence on alpha, alpha and beta, they carry the indices of the two bases. The first basis, the indices are omega Lm out in. I need the 4 indices. And the other basis only has 3 indices. Just tell you that the dependence on L and M is going to be Dirac delta, Kronecker delta. So alpha and beta, all of them are going to be proportional to delta Lm. So I'm going to suppress these indices from now on, just because otherwise I have to write too much. So they are there, but I'm not going to write them explicitly because that dependence is trivial. So if we are able to compute these coefficients, Hawking radiation will be at
Is
our
that
hand.
int there?
No, that is in. The int is here. I am writing the
But-
in one as a combination of the in.
Oh, okay, so
So I have two
that's
bases.
in up there too,
This-
okay.
This is
Yeah.
int, this is in. So this, the element of this basis as a combination of the other bases. Probably int and in are so close that people can get confused maybe. A different name is better.
Sorry.
No, it's okay. You can call them H or something rather than int. So all we have to do is to compute alpha and beta. If we have them, Hawking radiation will be automatic. Now, alpha and beta, as I said, is going to be the inner product. For instance, to compute any coefficient, alpha and beta, I need to take the inner product of this. For instance, if I want this coefficient, I have to take omega prime. That is going to be, I have to take the inner product of this guy, depending how I write it, out, and I have to multiply it by this term in omega prime, L prime, N prime, and I have to add a minus sign because the norm of this guy is minus. So I have to put that minus there. And remember that the inner product is always an integral in a Cauchy hypersurface. Doesn't matter which hypersurface, the inner product is the same, but they have to choose one. So the question is, which hypersurface do I choose to compute this? We have the Penrose diagram here. You can take any Cauchy hypersurface you want, cry minus, cry plus with the horizon, or any other one. Which one? We choose.
Minus.
Yes.
Minus plus.
Minus.
Why? Minus.
Because we know the values completely at square minus.
Because the in modes, they are very simple here. They are just positive frequency modes. But the out modes are positive frequency modes in sky class. So, to do that integral in sky minus, I would have to take a mode in sky class and propagate it back to here. If I choose a sky class, I have the same problem with the in modes. I have to take the in modes and bring them to sky class. So there is no easy choice. So whatever choice we choose, we are in trouble. We have to do the propagation. So there is no clear one. So following Hawking choice.
Okay, but what is that for? This I plus is not Cauchy hypersurface.
Right, you have to choose a sky class and the horizon together. But there is another. But you still have to propagate the in modes. Some of them will go to sky class, and the ones which are here will go to the horizon. Following Hawking original derivation. I choose a sky minus. There is a good reason for that, and I will explain it later. So then, therefore, we need to compute the form of the out modes in sky minus. So we have to take initial conditions for the out mode, and we know what they are. They are positive frequency modes here, and use the wave equation to propagate them backwards in time, and that is the main difficulty.
So It's an advantage to choose I minus because you don't have to know anything about int, right?
In particular. But you know, even if I choose Sky plus the horizon, if I am computing out, because the out modes, they don't have support in the horizon, the integral will be reduced to Sky plus only.
Oh, okay.
So, and if I want to compute beta int, then I only have to worry about the horizon.
Okay.
Hawking use Sky minus because the difficulties of propagating back in time get simplified with some arguments they will tell you later on. But now I don't even need to do that assumption because my spacetime is inverted there. And just tell you that it is at this point, for this calculation, where the approximations that I made of neglecting the potential are crucial and are extremely useful. So I'm going to get the wave equation, get the modes at the Sky class, positive frequency, and propagating backwards. And I insist the approximation that we made are going to be crucial here. You know, let me write the Venn diagram here. Remember, we have the ray producing the black hole, the null ray at B naught. This is what separates the Minkowski region from the Schwarzschild region, that line. And we have the horizon here. And I'm going to start propagating from Sky glass to V equal to V naught. So I'm going to propagate the modes from this hypersurface to this one, from this partial hypersurface to this one, just from here to here.
V naught is not that.
Sorry?
V naught was that or?
V naught was that.
that?
VH
Oh,
was,
VH was the other.
VH was this,
That
this V, which is the
Forms the horizon.
VH. Where
So,
the, what the
Yes,
side
forms the horizon.
when we propagate them back, we wouldn't have their form. I mean, they would only be from 0 to VH. Because,
exactly. I mean, but that is later on.
yes.
Right, that will happen. But first I'm going to propagate from here to here. And then I will continue going, but I'm going to do it step by step. So first step, propagation from I class to V naught. We are in Schwarzschild geometry, so we have to take the equation of motion in Schwarzschild geometry, give initial data here, and see what are the solutions in the past. And in principle, that is complicated. Remember that just to refresh your memory, the Klein-Gordon equation, which we have the expert here doing that. Only if you ask Peter, you know the result. But I am not Peter, so I will have to find a lazy way of solving this. Remember that the wave equation was something like that. So we have a potential here, and therefore the propagation is not trivial. But if you neglect the potential, the evolution is trivial. You know, solutions to this equation are e to the plus minus I omega u out. Remember, u out is just t out minus r out star. So you know, this guy remains solutions of this equation in the whole Schwarzschild region. Without the potential, the form of these guys here doesn't change in the whole evolution. So the evolution is trivial. And this is why I neglect the potential. But I will tell you in this next section what happens if you include the potential. That has to be done numerically. Since we have neglected V, the evolution in the Schwarzschild region is trivial. The out modes that we defined in a straight class, when evaluated at V naught, they are exactly the same as before. E to the minus I omega u out 4 pi root the square of omega spherical harmonics divided by I r. Again, I did this simple model of black hole precisely to be able to do what I am doing now analytically. Second step, we reached the division between Schwarzschild and Minkowski, so we have to use another solution in Minkowski and use matching conditions on that hyperstar. So now matching conditions at V naught.
And then we have to evolve phi int also, right?
Sorry?
We have to phi int,
But phi, we know what they are in sky minus. They were defined
they were defined.
in sky minus. The initial data was given in sky minus. So
it's-
you know, this is why I choose one or the other, because they are the simplest one. If I choose this one, I have nothing. I have to do nothing with the
Right.
in modes. If I choose this one, I have to do nothing with the out modes. If I choose something in the middle, then I am
What I mean
limited
is-
because I have to evolve both.
The the other modes, int modes.
But they don't. I mean, I need them to compute the int beta.
Yes.
But for compute the
this,
out, the out beta isn't there. So matching conditions. You know, the only thing we have to do is to write this as a function of u in. Remember, in the Minkowski region, we move from u out to u in coordinates. But the solution is trivial. This guy on the other side of V naught is just the same, but I have to write u out as a function of u in. But I know how to do that. I wrote the expression at the very beginning of the class. And I have also to write r out as a function of r in. But that is trivial because recall what I wrote at the beginning of the class. R in at V naught is exactly the same as R out at V naught. This was imposed by the matching conditions of the metric. And U out as a function of U in was given before. This logarithmic relation that I was writing at the beginning of the class. So we have that. Good. The only step is evolving back to experiment. That is maybe the less trivial part, because you know modes which are outcoming here, if you propagate them backwards in time, they are still outcoming, but they will be reflected at r equals 0. So you know, I want to do now propagation to a scribe class from V naught. You know, the difficulty here is that modes will be reflected. I write reflected in quotations because you know there is no real reflection. It's just if this is the origin of coordinates, a mode which is going out there, if you propagate backward in time, is going in. You know, in this plot, it seems that there is a mirror that like that is reflected at r equal now. So the modes which are outgoing, in the past they will be incoming. You know, they will do something like that. So in Minkowski region, the out modes will be a combination of outcoming or incoming modes. Combination of outgoing and ingoing. And my duty, my work has to be to determine which combination in particular. But there is a simple trick that you know. Remember, one of the conditions for the modes is that they have to be regular at r equals 0, because the modes always have a r in the denominator, so whatever goes in the numerator has to vanish at r equals 0, otherwise the modes will diverge. I will do it in some detail now. So regularity at r equals 0 will help to determine this. This is what I want. So what I want to say is that the out modes in the Minkowski region, this in the Minkowski region, is going to be a combination of outgoing modes, which are going to be as the ones that I wrote there, I omega u out as a function of u in. They only depend on u in that region, so they are outcoming, divided by r. Again, r is always r in or an r out, depending where we are. We are now in the Minkowski region, so this is. And now we have some coefficient c that may depend on many things, but it happens, it's going to be quite simple. Some function of v, I don't know which function, but because this guy only depends on v, I am sure it's an incoming wave. So my job is going to be determine what f and c are. And of course, I need here this stuff. Do you agree that I need here that? Remember, this is the horizon. This is pH. You know, if modes out are reflected, whatever is reflected is going to be have only support for V smaller than VH. Nothing reflected can have support for V larger than the VH. So the incoming part, due to the reflection, will carry that. Has to carry that. So I avoid that the incoming part has support in this region. So I have written this with the only condition that modes are a combination of out and incoming modes. Now, regularity will tell me what C and D is. I mean, regularity and also normalization. Regularity at r equals 0. First of all, C must be 1, already from the normalization. And regularity, remember that this line, r equals 0, is u in equal to v. This is what r equals 0 is. Remember that if you take the definition of u in and v, v is t minus plus r in, and u in is t minus r in, so r equals 0 is precisely what they are the same. So in order for this to cancel this with the minus there, this is forced to be the function out, this function, but replacing the u in by v. So where u out of v is obtained, I mean, trivially, you know, it's u out of u in replacing u in by b.
Why is c equal to 1?
Sorry?
Why is c equal to 1?
First of all, in order to get 0, and also because of normalization, you need c equal to 1. Both arguments give you. So therefore, we have the modes already straight lines. So the modes are going to be, the modes in the in region, in the Minkowski region, are going to be these ones with c equal 1 and So therefore, we conclude that the out modes at the scale plus, at the scale minus, are going to be one over 4 pi to the square of omega. And in fact, at the strike minus, remember strike minus is the boundary on plus infinity. At the strike minus, we never have outgoing modes. Modes, these modes are a combination of modes going in that direction. This is the first part, and modes incoming. But at the strike minus, we don't have these ones because they are tangential to a strike minus. So at the strike minus, we only get that part. Doesn't make sense to talk about outgoing modes in a strike minus because there is nowhere to go out. So that with the conditions that I just derived, u out as a function of v divided by r in, the spherical harmonic, with support only for v smaller than vh. Just a few steps that they are relatively simple, and now we have an exact expression, an analytical expression for out modes in a straight line. So we are ready to compute the probability coefficients. I just want to say a couple of things. Any question about this? About the derivation? So let me now open a parenthesis because before computing beta and mention something which is relatively important. So first of all, there are two. Let me see what is the behavior of these guys in two limits. One limit, these guys are only supported in this region. V is smaller than VH. So I want to see what is their behavior here and here. So in the region V going to minus infinity, these are the modes that will reach U close to, this is U out, from minus infinity to infinity. And if I take a mode, wave packet with support here, this wave packet will go to here. And I also want to study modes with support very close to VH, which are the modes that will go close to the horizon and will reach the infinity at late times, late U time. So what happens when V goes to minus infinity with these modes? Do you have a guess? Remember that at the beginning of the class, I remind you what are the limits of the relation between U out and U in. What happens with that relation? That was a logarithmic relation, but that relation was equal to U in when U out goes to minus infinity and was equal to the log, etc., when U out goes to infinity. But this is the same function. So when V goes to minus infinity, this guy is just V, and these modes behave. I forgot here an omega, sorry. I forgot that. Omega V. Again, because this function on that limit, because simply V. And, proportional, of course. All the other factors are there. I don't write them, 1 over 4 pi, etc. I'm just writing the important part. And on the other limit, remember, only the logarithmic part was surviving, minus I omega, VH, a constant, minus 2 RS log RS in the Schwarzschild radius, VH minus V over 2 RS. So this logarithmic relation between V and U out appears in the exponent. Can somebody tell me why is that relevant? You know, the two, what physically is going to produce this difference? The fact that, you know, that at every time the modes, the out modes are just this simple form, and close to VH, the out modes have this simple form.
Because they don't see the horizon and then they propagate as plane waves.
Right, these guys are very far from the horizon, so gravity doesn't affect them very much, and they reach scribe minus as a simple plane wave. But for the Hawking radiation, can somebody guess what is going to happen? Remember, my goal is to compute that, to compute the inner product of these guys, you know, this guy, with the in modes. But this is the in mode itself. I mean, this is a positive frequency in mode. And remember, the beta is the negative frequency component of this guy.
Right.
Which is zero, because it's a purely positive frequency mode with respect to scribe minus. So if when you compute that beta, beta out is going to be zero. Because phi out in scribe minus every time behaves as an exactly positive frequency in mode. It has no component of negative frequency in mode. But this is not going to be true for this guy. So for this guy, we can expect that, you know, this is going to be a combination of negative and positive frequency with respect to the time v. So this is going to be different. And as Rina was pointing out, is because, you know, modes which have support at v minus infinity, they evolve very far from the black hole. So the star is here, the black hole is there, they evolve really far from there, and doesn't care. But these other modes, they really evolve close to the horizon, and they pick this log, and we expect that. So, and remember, this beta has to do with particle creation. So this is suggesting, telling us that Hawking radiation in scribe class is only going to happen at late times. It's not going to happen at early times. And this can be just seen from this simple link. Yeah. This is telling to us that Hawking radiation only in scribe class, only for large values of the retarded time u naught. So the black hole forms, and only well in the future, after the black hole has been formed and has settled down, Hawking radiation will start appearing. Is that okay? Steven? You want me to expand? Why is that?
Okay, so time is larger as you go further along scribe plus.
Yes, this is the future always, because if you emit null ray, will propagate in one direction. So if null ray goes to the future.
Right.
So
Okay, so
this time is larger than this one. So time always goes like vertically here.
okay, time goes vertically, so that's why we say that
It's late times.
it's late times.
Right.
Okay, but it's also but the whole light ray passes close to the black hole horizon.
This one passes very close to the whole horizon.
So is that why they say that it's the black hole horizon where the effect happens?
I wouldn't say that.
Okay.
This happens because the black hole horizon. This logarithm log here, which is where the Hawking effect is going to come from, happens because of the black hole. But I wouldn't say that something particle creation happens at the black hole. I mean, the intuitive picture is that, but again, that is a huge extrapolation many times. So, okay, so when one computes Hawking radiation, then what we have to do is to take modes which only have support at late times, because modes with support at every times are going to be beta equals 0, and they are not interesting. But now is where we have to face the limitation of using plane waves. We are using plane waves for the out modes here, which are defined everywhere. So we cannot concentrate. Plane waves are very artificial. They are defined in the whole Hawking hypersurface. On the contrary, physical modes, if you have a photon will be concentrated. Will be a wave function concentrating there, or there. And the nice computation now here is done with wave packets which are which have support only on the late time region, and this is what I want to concentrate on because it's where Hawking radiation appears. But with plane waves, I cannot do that because they are defined everywhere. We have to face the limitation of plane waves. When I say plane waves, I mean they are really spherical waves. I mean that they are e to the I omega u out, so they are defined everywhere. So I have two choices. I start working with wave packets, which is complicated because I have to add an interval in omega there, or do a kind of trick to simulate the late time behavior. What I'm going to do, of course, is a trick. To simulate the late time behavior of modes that keep working with plane waves I'm going to use the late time limit of u out b. As I said, the reason why beta is 0 or non-zero is because how this function u out of b behaves. It behaves as v at early times and as a logarithm at late times. And this is crucial. So what I'm going to do is just use the logarithm relation as if I was at late times. So I'm going to replace the real behavior by the late time limit. Remember that the real behavior is like that, but at late times the log dominates at late times. When v goes to vh, which means that u out goes to infinity, this term dominates because this goes to 0, the log dominates over this, and this goes to a constant. So I'm going to use the late time expression as if I was working at late times, but keep working with plane waves. Of course, my result will only be valid for modes at late time. But it's a way of doing the right computation using plane waves without having to introduce wave packets, which are localized in some region. Did I communicate what is the problem and what is the trick? So sure I. So this part was clear. I have these modes, and they behave. You know, if you write, maybe you should. I should write what this is. U out of V is V plus 2RS log V H minus V divided by T. V minus V divided V H minus V.
V minus 2RS or
It's a line. And this behaves as, I don't have more space. When V goes to minus infinity, this term dominates, and this is negligible. So this is why the modes behave as a black net. This is why this reduces to V. At V close to VH, this term dominates. Because this goes to infinity and this gets finite. So this exponent gets this, where this is a constant. This is now a number, VH. So this is a trivial positive frequency mode here, so the beta coefficient is going to be 0. This is a non-trivial one, so the beta is going to be. So that tells me that only modes with support close to VH are going to have Hawking radiation. Modes with support at minus infinity are not going to have Hawking radiation. So in the future, Hawking radiation will be 0, and we will be building up, and we'll get a steady Hawking radiation at late times. And my goal is to compute Hawking radiation at late times. This is what I want to compute. So I want to focus on modes, mode functions, which have only support here. But plane waves are not good for that, because plane waves are defined everywhere. But I want to keep working with plane waves because they are so simple. So in order to simulate the late time behavior and still working with plane waves, I'm going to use only this portion. So technically speaking, I am using this in the whole range, which is false. That is only true in the, but I know that my computation is only right at late times, and in that way I get what I want. So it's a trick to use plane waves and compute what I want. Otherwise, you know, in next section I will tell you what happens with wave packets. But if I do the computation with wave packets, everything gets much uglier. So, if you are convinced on that, so as I said, we expect here no particle creation, and we expect here particle creation. So Hawking effect here, not Hawking effect here. So particle creation will be 0, and we will build in up until a steady flux of Hawking radiation. And these are precisely for modes which are very close to the horizon. Okay, so I'm going to work with this relation, but keep in mind that my computation is only true for late times. Now, with this, we can compute beta out. And I don't even need to do the whole computation. Remember the I didn't write. This guy is, as I said before, this is phi out. I just erase it. This is phi conjugated, omega prime, L prime, N prime. This by definition is minus I, the integral. I am doing an integral means chi minus, and the volume element is dv d theta r, or r squared, and I have now phi in partial v. In fact, as we were discussing 1 hour ago, this is what you have to do to the homework that I was asking last week. So you have the difficult part of the homework here written, and partial B out. And the statement is that this can be written, let me add one step. This can be written, I can integrate by parts and eliminate one of the terms at the expenses of having a boundary term. So if I integrate by parts, I have twice one of the two terms plus a boundary term. B r squared. And I have chosen to keep this in this way, partial B in omega prime, where the boundary term is 0 because the out modes in a scribe class, so the out modes don't have support in the boundary of scribe class. It's very nice. So they propagate backward in time and they don't have support neither here, neither in the boundary because they are now. I just wanted to give you this expression, and and now just plug here the out modes that we have here, these modes with the coefficients 1/4 pi omega, the spherical harmonics, and the same for the in modes, which are even simpler. And what you get is the following. An interval from minus infinity v minus infinity to ph, because the modes don't have more support, the out modes, they stop there, so the rest of the interval is exactly 0. I have already done the angular part and put outside all the omegas, etc., and I have already done the time derivative. And what is left is the exponents, vh minus 2rs log v minus vh divided 2rs from the out mode, and from the in mode minus I omega prime v. And this is multiplied by the Kronecker delta. Great. We have an explicit expression for the out mode. For the beta out. I don't need to do it in the interval. To derive the Hawking effect, this is all what I need. Is that clear? This here in the numerator appears because we are taking derivative of phi in, and that brings our omega prime in the numerator. But phi in, they also have our omega prime root square in the denominator. This is why this is simple. Similarly, oh, I forgot to say something. I just forgot to say that just a parenthesis, that remember the int modes that it was proposing at the very beginning, that they had a very weird looking. They are exactly, if you look this expression, they are exactly this expression extending v to v larger than vh. This is why somebody realized that that weird form of the int modes was appropriate, because it's just taking the out modes here and extending them over there. It was the same, but having this a minus sign there. So I forgot to mention that. Okay. The alpha coefficients, which are given by the corresponding inner product. they are given by this expression. Minus 1 over the root square of 2 pi omega prime divided by omega, and now an integral that I will write here. Integral dv minus infinity to vh e to the minus I omega dh 2rs. Very similar to that, except that there is a plus there. Plus I omega prime v. And that plus comes because here I don't have conjugate, and I add it there. Beta int. This is a bit long, but let me just write them, and we are done. All the computations are done, and we are ready to compute Hawking radiation. VH minus 2RS log V minus VH 2RS minus I omega prime V, and also multiply by, I forgot here the deltas. And the last one. Plus I omega prime V. Okay, we are done. The last thing I want to write, and I stop here, is that one can take these 4 coefficients manipulate these expressions a little bit. I mean, that will take me maybe 20 minutes or 15 minutes of manipulation, so I'm going to do it. You can try to do it just to show that these relations between the coefficients are true. And these relations are all what I need to compute Hawking radiation. As we can imagine, because in the Unruh effect, this is what happened. In fact, these relations are identical to what we had in the Unruh effect. Changing a couple of things. These are the relations that I wanted to do. And I want to close the section here. Just tell you that if you go to your notes of chapter 5, the Unruh effect, you will find the same relations replacing in the in modes by the Minkowski modes, the right Riller modes by the out modes, and the in modes by the left trigger modes, and replacing the acceleration of the observer by the Schwarzschild radius of the black hole, or 2 times the Schwarzschild radius of the black hole. Then, from now on, we only have to copy the results because it's exactly the same computation. So, in order to compute Hawking radiation, they compute how the in state is written in the in-out focus space. We just have to take the result from the Umbro effect and make those replacements. When you see acceleration, change it by twice the Schwarzschild radius, and we have the work done. So all the hard work was done here, and I know that going over a single detail is long, but I think the first time you see this is worth to do the computation in detail. And next day, what I will do is exactly that. Take the result from the Umbro effect and apply them here, because the work was already done.
So here you will trace out phi int.
Exactly. So phi int is going to be, in here is like the Minkowski modes, which are defined in the whole Minkowski spacetime. And there we had left and right modes, which we needed both to have. So here we have in and out. So these are the analogy. So we are going to express the Minkowski, the in vacuum in this focus space, and then trace out over this, and I will have a density matrix, which happens to be a thermal density matrix. Only remember for modes at late times, because I am doing that trace. So at late time, the in vacuum will be indistinguishable from a thermal state of outgoing radiation. So for somebody sitting here, the black hole is emitting particles with thermal spectrum. All the computations are done. So next day we will discuss the physics. So today class was a bit dry calculations, but now you have derived Hawking radiation. So next day we will discuss that and the physics. Okay.